Our universe might be just one page in an infinite cosmic library. The idea of the multiverse suggests that every possible reality exists somewhere, but this cornerstone of modern physics is far more fragile than it seems. We are about to explore 24 concepts that could completely collapse this understanding. You will walk away seeing the cosmos in a radically new light, questioning the very nature of reality itself. What if the rules for creating universes need their own rules, starting a chain that never ends? Could our entire existence be a statistical fluke in a sea of nothingness? This journey will take us from the deepest puzzles of quantum mechanics to the edges of observable space, revealing why the multiverse may be science's most captivating dead end. Are you ready to have everything you thought you knew about parallel worlds turned inside out? Every explanation must eventually rest on an unshakable foundation, but the multiverse theory seems to have no solid ground. Think of it like a set of Russian nesting dolls, where each layer reveals another, smaller version of itself, continuing into an endless, dizzying descent. This is the problem of infinite regress, a philosophical trap that threatens to unravel the entire multiverse concept at its very first step. If the multiverse contains every possible version of reality, who or what wrote the rulebook for what is possible? The laws of physics that govern our universe, like the strength of gravity or the mass of an electron, appear finely tuned. The multiverse offers an answer, suggesting that in an infinite array of universes, a cosmos like ours with life-friendly constants was bound to appear by chance. Yet this simply pushes the mystery back one step. What determines the set of all possible laws? To explain the multiverse, we would need a meta-theory, a set of rules that dictates which types of universes can be born. But then we must ask, what are the rules for that meta-theory? This begins a chain of reasoning that has no end, an infinite tower of explanations, each requiring another. As physicist Brian Greene has noted, even our leading theory for how a multiverse would be generated, cosmic inflation, fails to explain why the inflationary field itself has the properties it does. The multiverse does not answer the ultimate question of why there is something rather than nothing. It merely relocates the question to a higher, more abstract level, leaving us with a cosmic shrug. This logical dead end is not just a philosophical curiosity. It points directly to a tangible, physical limitation in our observations of the cosmos, a puzzle known as the horizon problem. This logical descent into infinite regress finds a physical echo at the very edge of what we can see. Our cosmic vision is bounded by a horizon, a final frontier beyond which light has not had enough time to reach us since the Big Bang. Think of this cosmological horizon as the ultimate one-way mirror. We can see the afterglow of creation from our side, but we can never know what, if anything, lies beyond its shimmering surface. In the multiverse theory, this horizon is not just the edge of our universe, but the wall of our cosmic prison. Other universe bubbles, born from the same inflationary energy, are perpetually receding beyond this boundary, forever out of reach. They are causally disconnected from us, meaning no signal, no particle, no shred of information can ever cross the void to confirm their existence. This presents a profound challenge to the entire scientific method. How can we test a theory about realities that are, by their very definition, untestable? The great physicist Stephen Hawking spent decades wrestling with a similar problem, the black hole information paradox. He realized that when something falls into a black hole, the information that described it seems to be permanently lost from our universe, violating a core principle of physics. The multiverse presents an even grander version of this paradox. If an infinite number of universes are constantly being born, but their properties are forever hidden behind an unbreachable horizon, then the information about them is fundamentally lost to us. The multiverse begins to look less like a scientific theory and more like a modern myth. A story that might be elegant or compelling, but one that can never be verified or disproven. A theory that predicts every possible outcome ultimately explains nothing at all, because any observation can be dismissed as mere coincidence within an infinite ensemble. This crisis of falsifiability forces us to confront an even deeper question about the supposed variety of these hidden worlds, a question concerning the very laws that would govern them. Even the vacuum of space is not what it seems. In the quantum world, absolute emptiness is an illusion. What we call the void is a vibrant, bubbling sea of potential, where particles flicker in and out of existence in a heartbeat. This quantum foam has a property known as its vacuum energy, a fundamental baseline energy level that can, astonishingly, exist in different states. String theory, our most ambitious attempt to unify all forces of nature, paints a picture of this vacuum that is almost impossible to comprehend. It suggests there is not one true vacuum state, but a colossal number of them. A number so vast it dwarfs the count of atoms in our observable universe. This is the string theory landscape, a cosmic terrain of 10 to the 500th power possible configurations for the vacuum. Each valley in this landscape represents a different set of physical laws, a different possible universe. This immense variety is often presented as the ultimate support for the multiverse. With so many options, of course, a universe like ours would appear. But this very abundance creates a profound crisis of explanation. If there is no single, unique, lowest energy state that nature prefers, then there is no fundamental reason why our universe has its specific constants. The strength of gravity, the mass of an electron, these are not dictated by a deep, elegant principle. They are merely the random coordinates of our cosmic address within an infinite landscape. The theory offers no prediction, only a post facto selection from an unimaginable menu of possibilities. As the physicist Paul Davies pointed out, when a theory allows for everything, it explains nothing. The fact that we find ourselves in a life-permitting universe becomes a trivial coincidence, a statistical inevitability in an ensemble where every possible outcome is realized. This arbitrariness strips science of its power to answer why, leaving us with a hollow victory. If the multiverse is built on such a shaky foundation, how can we ever hope to measure or confirm its existence? This pushes us directly into one of the most stubborn puzzles in all of physics. The same quantum weirdness that fills the void with potential also lies at the heart of reality's most famous feline paradox. Schrödinger's cat, trapped in a box with a quantum-triggered poison, is the unsettling icon of a universe that refuses to make up its mind until we look. This is the quantum measurement problem, the deep mystery of what actually causes the shimmering cloud of possibilities to snap into a single, solid fact. If you think the answer is simply that we need an observer, you are stepping into a hall of mirrors. Who qualifies as an observer, a scientist, a camera? A single atom? This line of questioning quickly leads to philosophical chaos. To escape this, the many worlds interpretation makes a breathtakingly bold claim. It says there is no collapse. At the moment of the experiment, the universe does not choose. Instead, it splits. In one reality, the cat lives. In another, the cat dies. Both are equally real, branching off from each other in a constantly dividing tree of existence. This seems to solve the measurement problem elegantly by declaring it an illusion. There is no mysterious collapse because every possible outcome simply happens somewhere. But this elegant solution comes with a staggering price tag. It demands the continuous creation of an infinite number of new, complete universes every nanosecond, for every quantum event everywhere. This is a multiverse generated not by cosmic inflation, but by endless choice. And this leads to a crushing violation of Occam's razor. The principle that the simplest explanation is usually the best, proposing a near infinite number of unobservable universes to explain the quirks of our single, observable one seems like the least simple solution imaginable. As physicist John Wheeler quipped, "It's like theorizing an entire, invisible jungle to explain the rustling of a single leaf. An even stranger problem emerges from within the theory itself." If every possible outcome occurs, then what does probability even mean? In our world, we say a radioactive atom has a 50% chance of decaying in the next hour. But in the many worlds view, it will decay in half the branches and will not in the other half. So why do we experience the flow of time as a sequence of likely events? Why does it feel like we are on a probable branch, rather than constantly finding ourselves in the one in a trillion universe where incredibly unlikely things happen all the time? The theory struggles to explain why our conscious experience seems to align with statistical likelihood, a ghost of probability that haunts a reality where everything is certain. This internal conflict within a leading quantum theory reveals a deep crack in one of the multiverse's foundational pillars. If the solution to a quantum mystery requires spawning countless realities, then the fine-tuning of our own universe becomes an even more perplexing artifact. Are we simply the lucky branch where the constants of physics allowed for stars, planets, and life? Or is this delicate balance pointing toward a completely different kind of truth? One that suggests our universe is not just one possibility among infinite others, but something far more significant and rare. The universe appears to be a perfect cosmic habitat, a sanctuary with its physical laws set to an almost impossible precision. If gravity were only marginally stronger, every star would burn through its fuel in a fleeting moment, collapsing into black holes before life could even dream of beginning. If the force binding atomic nuclei were slightly weaker, the complex elements that form planets and people would never have been forged in stellar furnaces. This is the fine-tuning problem, a mystery that has captivated physicists for decades. The multiverse seems to offer the perfect, almost lazy, solution. If an infinite number of universes are constantly bubbling into existence, each with its own random set of physical constants, then it is no surprise we find ourselves in one of the rare, habitable ones. This line of reasoning is known as the Anthropic principle. It states that the universe must be compatible with the conscious life that observes it. On the surface, it feels satisfying. But look closer, and you will see a profound logical flaw. This is not an explanation, it is a tautology, a circular argument dressed up as science. It is like a lottery winner claiming their victory is not surprising because someone had to win. The real mystery is not that a particular ticket was drawn, but why the lottery exists at all. By invoking the Anthropic principle, the multiverse theory uses our own existence as its sole piece of evidence, a classic case of selection bias. We are only here to notice the fine-tuning because the tuning was just right. This reasoning effectively halts further investigation. Instead of asking why the laws of physics are what they are, we are told it is a meaningless question, a random roll of the cosmic dice. But science thrives on why questions. Accepting the Anthropic principle as a final answer risks collapsing a grand scientific theory into a philosophical dead end. A story that explains everything and therefore nothing. This reliance on circular logic points toward a deeper flaw, one rooted in the very mathematics used to justify the multiverse in the first place. A universe exactly like our own, down to the last atom, must exist somewhere in the infinite multiverse. But so does a universe almost identical to ours, except the coffee you drank this morning was slightly colder, and another where it was infinitely colder. When every conceivable configuration is not just possible but guaranteed to exist, the simple idea of probability shatters. How likely are you to find your specific universe? The answer becomes meaningless. In an infinite ocean, what is the probability of finding one particular drop of water? It is effectively zero. Yet, by the same logic, the probability of finding a drop of water is 100%. This is the paradox of uncomputable probabilities. Mathematicians call this a measure problem. To calculate a probability, you need a sensible way to measure one set of outcomes against all possible outcomes. But in a truly infinite multiverse, how do you count? Imagine trying to determine if odd numbers are more common than even numbers. At first glance, they seem equally abundant. But what if you group the numbers differently? Consider the set of all numbers, 1, 2, 3, 4, and so on. Now, for every even number, include the next two odd numbers. Suddenly, it seems there are two odd numbers for every one even number. In an infinite set, the way you slice and dice the possibilities changes the answer completely. There is no single correct way to define what is typical or rare. This is not an abstract puzzle. It strikes directly at the multiverse's scientific credibility. The theory's main selling point is that it explains the unlikely fine-tuning of our cosmos as a statistical inevitability. But if we cannot define what likely even means, the argument collapses. We are left with a theory that cannot make a single testable prediction. It can only state after the fact that whatever we observe must have happened somewhere. A scientific model that offers no forecasts, only postmortems, is no longer doing science. It becomes a narrative, a story we tell about the cosmos that is completely detached from the mathematical rigor that birthed it in the first place. This deep mathematical flaw suggests that infinity might be more than just a challenging concept. It might be a warning sign that we are asking the wrong question about the very fabric of existence. Perhaps the most unsettling escape from the fine-tuning puzzle is the possibility that there is no puzzle at all. The laws of physics might not be deep, mysterious truths waiting to be discovered. They could simply be lines of code. This is the simulation hypothesis, the idea that our universe is not base reality but an artificial construct, a digital simulation running on a computer of unimaginable power. If this is true, then our entire scientific quest takes on a bizarre new meaning. The quest for a theory of everything, a set of equations that describe all of existence, becomes analogous to a character in a video game trying to reverse engineer the game's engine. They might successfully deduce the rules governing gravity or collision detection within their world, but they would be completely missing the point. Those rules are not fundamental laws of nature. They are arbitrary choices made by the programmers. The cosmic speed limit of light, the strength of the nuclear forces, the delicate balance that allows for life. All of these could be adjustable parameters, set to their current values for reasons we cannot possibly comprehend. In this scenario, the multiverse theory undergoes a radical shift. The vast landscape of possible universes with their different physical constants would not be a feature of ultimate reality. It would be a feature of the simulation's design. Perhaps the simulation is designed to explore different cosmological parameters. Or maybe our universe is just one server among countless others in a cosmic data center. The multiverse would be real in a sense, but its existence would be a consequence of engineering, not physics. This hypothesis does not so much collapse the multiverse as it collapses the significance of our search for it. We would be like ants meticulously mapping the grooves in a vinyl record, unaware that the music we hear is an emergent property of a technology far beyond our comprehension. This forces a confrontation with the most elusive element of our reality, the very thing that makes the fine-tuning problem meaningful in the first place: consciousness itself. The most intimate evidence we have for reality is the simple fact that we are experiencing it. You feel the warmth of the sun, the weight of a thought, the sting of disappointment. This raw, subjective awareness is consciousness, and it presents the single greatest challenge to a purely physical description of the world. Why should a particular arrangement of atoms, no matter how complex, give rise to the inner world of feeling. This is the hard problem of consciousness, and it stubbornly resists any explanation that relies solely on neurons firing or computations running. Some philosophers and scientists argue we have been looking at the problem backwards. Perhaps consciousness is not a late arriving guest at the cosmic party, emerging from the intricate dance of matter. Perhaps it was the host all along. This idea, known as Panpsychism, proposes that consciousness is a fundamental property of the universe, as basic as mass or charge. In this view, even the simplest particles possess a tiny spark of experience, a dim proto-feeling. Complex systems like our brains don't generate consciousness from scratch. Instead, they organize and amplify these fundamental bits of awareness into the rich stream of thought we know. Now, consider what this does to the multiverse theory. If consciousness is primary, then the vast landscape of possible universes, each with its own random set of physical constants, becomes a secondary phenomenon. The multiverse is no longer a mindless, mechanical froth of bubble universes. It might be better understood as a vast tapestry of experiences, a multiverse of minds. The fine-tuning of our cosmos is not a lucky draw from a cosmic lottery. It could be the necessary physical expression for a certain kind of conscious experience to unfold. This completely inverts the standard scientific story. We are not insignificant observers in a lucky universe. Instead, the entire physical cosmos, with its specific laws, might be the way a fundamental consciousness chooses to express and understand itself. This perspective doesn't just add another layer to the multiverse debate. It threatens to collapse the very motivation for it. Why do we need an infinity of unseen worlds to explain the peculiarities of our own, when the answer might lie in the nature of the one thing we know for certain exists, our own awareness? This philosophical shift forces a critical re-examination of the hard data from our telescopes, the evidence that supposedly points toward a multiverse in the first place. Our most powerful telescopes have scanned the heavens for generations, collecting petabytes of data from the faintest whispers of starlight. Yet in all this cosmic noise, there is a profound and telling silence. No signal, no anomaly, no definitive message has ever arrived from beyond the boundary of our own universe. The multiverse remains a ghost, a theoretical specter haunting the edges of our equations. Science, at its core, is built on a foundation of observation. A theory can be mathematically beautiful, intellectually compelling, but without empirical evidence, it remains a captivating story, not a confirmed description of reality. The primary support for the multiverse comes from its consistency with other ideas, most notably cosmic inflation. The theory that our universe underwent a period of unimaginably rapid expansion just after the Big Bang. Inflation elegantly solves several major cosmological puzzles, and the mathematics suggests that once this inflationary energy gets started, it might be eternal, continually spawning new universe bubbles. But this is an inference, a chain of reasoning. It is not the same as seeing another universe. The closest we have come to potential evidence lies in the oldest light we can see, the cosmic microwave background radiation. This faint glow is the cooled remnant of the Big Bang's fireball, a baby picture of the cosmos. Some scientists have searched this map for strange patterns, like circular bruises that could be scars from a long-ago collision with another inflating universe bubble. While a few intriguing anomalies have been spotted, none have held up to rigorous scrutiny. They could just as easily be statistical flukes or artifacts of how we process the data. The debate surrounding these features highlights the problem. Without a clear, unambiguous signature, every potential clue remains in the realm of speculation. This evidentiary drought has led some prominent physicists to dismiss the multiverse as not even wrong. This famous phrase, coined by Wolfgang Pauli, describes an idea that is so vague and flexible it cannot be tested. A scientific theory must be falsifiable. It must make predictions that could, in principle, be proven false by an experiment. If a theory is compatible with every possible outcome, it has no scientific weight. If we find a cold spot in the cosmic microwave background, it could be evidence of a multiverse. If we do not find a cold spot, that is also consistent with the multiverse, because perhaps the collisions are rare or the signatures are different. When a theory accounts for everything, it ultimately explains nothing. This reliance on theoretical elegance alone, in the absence of hard data, marks a critical weakness. It pushes the multiverse dangerously close to the edge of science, into a territory where belief begins to overshadow proof. The very framework that gave us the multiverse landscape is itself cracking under the weight of its own ambition. String theory began with a beautiful promise to be the final theory of everything. It proposed that if we could peer into the heart of an electron or a quark, we would not find a point, but a tiny, vibrating loop of energy. The different vibrations of this string would manifest as all the particles and forces we see in nature. A cosmic symphony written in one fundamental note. This elegant idea naturally gives rise to the landscape of 10 to the 500th power possible universes. But after decades of intense work by the world's brightest minds, that symphony has fallen silent. The theory has failed to produce a single, unique prediction that we can test with our particle accelerators or telescopes. The energy scales needed to see these strings directly are astronomical, far beyond what any technology we can conceive might ever achieve. We are like listeners trying to discern the shape of a violin by studying the echo of its music from 1,000 miles away. The result is a crisis of credibility. If the theory that predicts the multiverse cannot itself be verified, then the multiverse begins to look like a castle built on clouds. This has led to a quiet but growing rebellion within theoretical physics. Some researchers are now openly questioning if we have been walking down a dead-end path for 50 years, chasing mathematical beauty at the expense of physical truth. They argue that a theory, no matter how elegant, must eventually connect to the real world. Without that anchor, string theory risks becoming a self-contained mathematical fantasy, and the vast multiverse it implies becomes little more than a compelling footnote in that fantasy. This foundational weakness forces us to confront a much simpler, almost brutal, argument against the entire multiverse enterprise. The simplest explanation is often the one that cuts closest to the truth. For centuries, scientists have wielded a powerful intellectual tool known as Occam's razor, a principle that favors solutions requiring the fewest new assumptions. When faced with a mystery, the hypothesis that introduces the least amount of speculative baggage is usually the most promising path forward. The multiverse theory, in its breathtaking ambition, seems to throw this principle out the window. To account for the peculiarities of our single, observable cosmos, it makes the most extravagant assumption imaginable: the existence of an infinite number of other, entirely inaccessible universes. It proposes a reality of such stupefying vastness that it makes our entire cosmic horizon seem like a single grain of sand on an endless beach. Critics point out that this is the very definition of an unparsimonious explanation. It is like trying to explain a single misplaced house key by proposing the existence of an infinite number of identical, invisible houses. The key is not lost, you simply cannot see the correct house. This might technically be a possibility, but it is hardly a helpful or elegant solution. The multiverse answers the question of why our universe is the way it is by effectively saying, "Do not worry. Every other possibility is also real somewhere else." This does not feel like an explanation. It feels like a surrender. Of course, Occam's razor is a guideline, not an unbreakable law of logic. There are times in science when the correct answer is, counterintuitively, the more complex one. The shift from an Earth-centered solar system to a Sun-centered one initially seemed more complicated. but it ultimately provided a simpler, more unified explanation for the motions of the planets. The multiverse, however, struggles to offer that kind of unifying power. It adds an almost infinite layer of complexity without delivering a corresponding increase in explanatory clarity. It tells a grand story but fails to simplify the plot. This philosophical preference for simplicity leads us directly to a quantum-level puzzle that offers a far more restrained, and perhaps more convincing, account of reality. The quantum world does not need a conscious observer to force its hand. A single atom isolated in a perfect vacuum can exist in a shimmering state of multiple possibilities, a true superposition. But our world is not a perfect vacuum. It is a messy, bustling environment filled with trillions of particles constantly bumping and interacting. This relentless chatter is the key to a process called quantum decoherence. When a quantum system, like the fate of Schrödinger's cat, interacts with even a single photon from the environment, its delicate wave of possibilities becomes entangled with the outside world. The information about its state leaks out, spreading at the speed of light. From our perspective, the superposition appears to vanish, collapsing into a single, definite outcome. But nothing has actually collapsed. The cat is either alive or dead. The universe has simply chosen a path, and the alternative possibility has faded from view, not because a physicist opened the box, but because the environment effectively did it first. This process of decoherence provides a powerful, elegant explanation for why we experience a concrete reality, not a blur of quantum mayhem. It happens constantly, everywhere, without any mysterious conscious observation required. This single idea delivers a devastating blow to one of the strongest arguments for the many worlds multiverse. If decoherence can explain the illusion of wave-function collapse through perfectly ordinary quantum interactions within our one universe, then why do we need to invoke the continuous creation of an infinite number of parallel realities? The primary motivation for that breathtakingly vast multiverse was to solve the measurement problem. If that problem has a simpler, more localized solution, the entire branching tree of many worlds begins to look like an unnecessary extravagance. It is the difference between explaining a magician's trick by revealing the hidden mirror, and explaining it by proposing that the rabbit actually vanishes into another dimension. One explanation is grounded in the mechanics of our world. The other requires rewriting the nature of reality itself. By focusing our attention back onto a single, coherent cosmos, decoherence opens the door to a far more restrained and perhaps more profound vision of our place in the universe. Our universe might not be an isolated bubble in an endless foam, but a single, eternal heartbeat. This is the promise of the cyclic model, a vision where the cosmos dies only to be born again in a new form. In Roger Penrose's conformal cyclic cosmology, the end of time is not a cold, dark emptiness. As the universe expands forever, all matter eventually decays into radiation, and black holes evaporate, leaving a vast, featureless sea of light particles. In this state, the concept of distance and time loses all meaning. The universe becomes smooth, simple, and in a profound mathematical sense, identical to the ultra-smooth, ultra-simple state of the Big Bang. The end of one eon becomes the beginning of the next, in an unending cycle of renewal. This is not a multiverse of parallel worlds existing at the same time. It is a serial multiverse, a single reality living countless lives, one after another. This elegant idea solves one of cosmology's deepest puzzles, the low entropy problem. Why was the early universe in such an extraordinarily ordered, low entropy state? In the cyclic model, it is because our universe was born from the highly ordered death of its predecessor. The smooth, featureless end of the last eon naturally provides the smooth, simple starting point for our own. This offers a powerful alternative to cosmic inflation, sidestepping the need for an eternally breeding multiverse. If the cosmos is cyclic, then the search for other universes is not a journey outward into an invisible expanse, but a journey forward in time, waiting for our own universe to complete its grand transformation into the next. Such a cyclical nature forces a dramatic rethinking of cosmic history, and with it, the ultimate fate of all information. The same energy that births universes condemns them to a slow, cold extinction. Eternal inflation paints a picture of a cosmos in a state of perpetual creation, a fountain endlessly spouting new bubbles of reality. Yet within each of those bubbles, the story is one of inevitable decay. Every universe, including our own, is on a one-way trip toward heat death, a final state of perfect equilibrium where energy is evenly distributed, no stars shine, and no work can be done. The multiverse, in this view, is not a vibrant garden of possibilities. It is a vast and ever-expanding cemetery, where for every one universe flickering briefly with light and life, an infinity of others exist in a state of permanent, frozen darkness. This presents a profound existential paradox. The theory invoked to explain the lucky accident of our habitable world does so by placing it in a context where lifelessness is the overwhelming norm. Our vibrant cosmos becomes a statistical fluke, a single glowing ember in an endless sea of cold ashes. Does this truly explain our existence, or does it merely bury its significance? If the ultimate fate of nearly all reality is a silent, featureless void, then the multiverse does not enrich our understanding of the cosmos. It threatens to diminish it, transforming a universe filled with wonder into a temporary and cosmically insignificant anomaly. This focus on the final state of disorder, entropy, connects to a deeper principle about the nature of information itself, and what might be permanently lost in the void. Black holes present a terrifying paradox. They are the ultimate vaults, swallowing matter and light, seemingly erasing all information about what fell in. Yet quantum mechanics insists that information can never be truly destroyed. The resolution to this paradox gave birth to one of the most startling ideas in modern physics, the holographic principle. It proposes that all the information describing the three-dimensional volume of a black hole is not lost inside, but is perfectly encoded on its two-dimensional event horizon, the point of no return. Think of it like a cosmic DVD. The movie you experience is a rich, three-dimensional world, but all the information needed to create it is stored on the two-dimensional surface of the disk. Our universe itself might operate on the same principle. The three-dimensional reality we inhabit, with its galaxies, planets, and people, could be a projection from a vast, two-dimensional surface at the edge of the cosmos. This is not just a quirky analogy. It is a serious proposal that redefines the very nature of space and information. If the holographic principle is correct, it places a fundamental limit on how much information any region of space can hold. There is a maximum data density for reality. This creates an immediate and severe problem for the infinite multiverse. An endless collection of universes would require an infinite amount of information to describe all their varied laws, particles, and histories. But a holographic cosmos has a finite data budget. It cannot accommodate an infinite ensemble. The multiverse, in its standard form, would be mathematically impossible. The principle suggests a radical alternative. What if the entire multiverse is not a collection of separate three-dimensional bubbles, but a single, unified projection from a deeper, two-dimensional reality? The different universes would not be physically distinct places. They would be different sets of data encoded on the same cosmic hard drive, like different files on a computer. This would completely collapse our standard picture of the multiverse as a vast expanse of parallel worlds. Instead of an infinite spatial foam, we would have a finite informational structure. The quest to understand the geometry of this fundamental surface leads directly to a different kind of puzzle, one that questions the stability of the vacuum from which all universes are thought to spring. Our reality might be a three-dimensional island adrift in a much larger sea. The Brane multiverse idea takes the strangeness of string theory and pushes it into a new dimension, literally. In this picture, our entire cosmos, with its galaxies, stars, and planets, is not the whole story. It is a three-dimensional membrane, or brane for short, existing within a higher dimensional space called the bulk. Think of our universe as a single, impossibly thin slice of bread floating inside a cosmic loaf. Other slices, other branes, could be floating right alongside ours, each one a complete, separate universe with its own laws of physics. These parallel worlds could be mere millimeters away from us in a direction we cannot perceive. A collision between two such branes could even be the real cause of the Big Bang, a titanic clash of realities that birthed our own. This is a compelling and visually striking model, but it rests on a foundation that has proven frustratingly elusive. The entire concept depends on the existence of extra-spatial dimensions beyond the three we experience. We are familiar with length, width, and height. The Brane multiverse requires these dimensions to be curled up, or compactified, into shapes so tiny we have not yet detected them. For decades, physicists have searched for any sign of these hidden dimensions. They have looked for particles that might momentarily vanish into them, or for subtle deviations in the force of gravity at microscopic scales. So far, every search has come up empty. The extra dimensions remain a beautiful mathematical possibility, but a complete physical mystery. This is more than just a missing piece of evidence. It is a potential deal breaker. If we ultimately confirm that no extra dimensions exist, the entire Brane multiverse model collapses into pure speculation. The mathematics behind these Brane worlds is also notoriously fragile. To create a stable, realistic universe like ours, the equations require an astonishing degree of fine-tuning. The properties of the brane, the shape of the extra dimensions, the forces acting within the bulk, all must be balanced with a precision that rivals the very cosmic fine-tuning the multiverse was supposed to explain. We are left chasing our own tails, using one form of unexplained, delicate balance to account for another. This internal inconsistency reveals a deeper pattern in the multiverse quest. A proposed solution to one profound mystery often just creates a new, equally profound mystery of its own. The search for these hidden dimensions forces us to ask a fundamental question about the nature of space itself. Is our geometric intuition, built from a life in three dimensions, simply incapable of grasping the true architecture of reality? Or are we projecting a mathematical fantasy onto the cosmos? This geometric puzzle finds a surprising parallel in the quantum world, where the very act of observation might be shaping the reality we seek to measure. Our physical reality might not simply be written in the language of mathematics. It might be the language. Max Tegmark's mathematical universe hypothesis pushes the idea of the multiverse to its absolute logical extreme. It proposes that every structure that is mathematically consistent, that can be described without internal contradiction, must exist as a physical reality. This is not a multiverse of different physics. It is a multiverse of different mathematics. Think of every possible geometric shape, every conceivable number system, every abstract pattern of logic that a mind could dream up. In this view, they are all out there, somewhere, as real as the universe you and I inhabit. A cosmos governed by the rules of Euclidean geometry exists alongside one running on hyperbolic principles. A reality where 2 + 2 = 5 is not wrong. It is simply operating under a different set of axiomatic truths. This is the ultimate democratization of existence, where every mathematical idea gets its own cosmic canvas. But this radical inclusivity comes at a devastating cost. If every mathematical structure is real, then the word real begins to lose its meaning. Our universe, with its specific, tangible laws, becomes just one entry in an infinite library of abstract possibilities. The concept of a universe collapses under the weight of its own generality. What separates a real, physical world from a mere equation on a page when the equation is declared to be the world? The hypothesis faces an even more fundamental challenge, one that strikes at the heart of the scientific method. It is, by its very nature, untestable. There is no experiment we can design, no observation we can make, to confirm or deny the physical reality of a universe based on a mathematical system alien to our own. It exists in a realm forever beyond empirical reach. This moves the discussion from the domain of physics into the realm of pure metaphysics, a philosophical stance about the nature of being. It answers the question of why there is something rather than nothing by stating that nothingness is mathematically inconsistent, and therefore impossible. But for many scientists, a theory that cannot be falsified is not a theory at all. It is a belief. This flight into pure abstraction stands in stark contrast to a very specific, very tangible feature of our own cosmos, a feature that seems to whisper of a much simpler, more unified origin. The cosmic background radiation should be a perfectly random tapestry, a relic of the primordial chaos that birthed our universe. Instead, it holds a strange and unsettling signature, a pattern so unexpected that scientists half-jokingly named it the axis of evil. When the most detailed maps of the cosmic microwave background were first created, researchers expected to see a gentle, random distribution of hot and cold spots, the fading imprint of quantum fluctuations from the universe's first moments. But the data revealed something else entirely. The largest temperature fluctuations across the sky are not randomly scattered. They appear to align along a preferred axis, a kind of cosmic equator that seems to defy the foundational principle of cosmology, the idea that the universe is isotropic, meaning it should look the same in every direction. This is not what a universe born from a featureless, inflationary burst should look like. It is as if you threw a bucket of paint at a wall, and it landed as a perfect, structured mural. For proponents of the multiverse, this anomaly was electrifying. Perhaps this axis is not a flaw in our data, but a cosmic scar. It could be the bruise left by a collision with another universe bubble in the vast inflationary foam, a glimpse of a reality beyond our own. Yet, after years of intense scrutiny, the mystery persists, and its implications for the multiverse are far from clear. The simplest explanation is that the axis of evil is a statistical fluke, a trick of the data caused by the way we filter out the foreground glow of our own galaxy, or perhaps an unaccounted-for instrumental error. If this is the case, then a tantalizing piece of potential evidence for the multiverse simply evaporates, but the plot thickens. Even if the anomaly is confirmed as a real feature of the cosmos, it does not automatically point to a multiverse. Alternative theories, ones that modify the standard inflationary picture or even challenge the Big Bang itself, could potentially account for this large-scale alignment without ever invoking an infinite number of parallel worlds. The fate of these cosmic quirks is a pivotal battleground. They represent a critical test. If the multiverse is to move from philosophical speculation to scientific theory, it must make predictions that are confirmed by observation. The axis of evil presented a perfect opportunity, a potential fingerprint of another universe. Its ambiguous and controversial nature, however, leaves the multiverse hypothesis in a precarious position, still searching for its smoking gun. This struggle to find a unique signature in the heavens forces a much deeper question, one that goes back to the very beginning of everything. The initial singularity is a point where all our theories fail. It represents a moment of infinite density and temperature, a boundary beyond which physics as we know it ceases to function. The multiverse, particularly the idea of eternal inflation, appears to offer a graceful escape from this cosmic cul-de-sac. It suggests our Big Bang was not the absolute beginning, but merely a local event within a much larger, eternally existing meta-universe that has always been spawning new bubbles. This seems to solve the problem of a definitive start, but the solution is an illusion. We have simply traded one mystery for another. The haunting question, what happened before the Big Bang, is not answered. It is merely rephrased as, what caused or set up the state of eternal inflation in the first place? If the meta-universe is truly eternal, stretching infinitely into the past, then we are faced with the philosophical absurdity of an infinite regress of time, an endless chain of cause and effect with no first cause. If it had a beginning itself, then we are back at square one, needing an explanation for its origin. The multiverse does not remove the need for an ultimate beginning. It merely hides it behind a veil of cosmic complexity. This relentless pursuit of a first cause inevitably brushes against the realm of theology. For centuries, the cosmological argument for a divine creator has rested on this very point, that the chain of causality cannot extend backward forever and must have an uncaused first cause. The multiverse, in its attempt to provide a purely physical explanation for existence, inadvertently resurrects this ancient debate. It forces us to confront the possibility that the question of origins may lie outside the domain of science altogether, in a territory where physics meets metaphysics. By failing to provide a final answer, the multiverse theory highlights the profound limits of our current understanding, suggesting that the ultimate nature of reality might be a mystery that forever eludes our grasp. The multiverse was supposed to silence one of humanity's oldest debates, but it may have only amplified the question. For centuries, the uncanny precision of the cosmos has been cited as evidence for a grand designer, an argument from design pointing to intentional fine-tuning. The multiverse offers a powerful rebuttal. If every possible universe exists, then a life permitting one like ours is inevitable, a statistical certainty requiring no architect. Yet this elegant dismissal contains a hidden trap. What if the mechanism that creates the multiverse is itself finely tuned? Consider the engine of eternal inflation, the quantum field that supposedly spawns infinite bubbles. For this process to work, the laws governing that field must be set with exquisite precision. The rules of quantum mechanics that allow for superposition and branching, the specific energy landscape of string theory, these are the meta-laws that make a multiverse possible. They are the fundamental code of the cosmic generator. And if that code were even slightly different, the entire multiverse apparatus might fail to start, or it might produce only barren, lifeless voids. This realization turns the tables completely. The multiverse does not eliminate the need for a first cause or a fundamental order. It simply pushes it back one level, from the fine-tuning of our universe to the fine-tuning of the multiverse generator. We are right back where we started, facing the same profound mystery of why the foundational rules of reality are what they are. This is not a scientific argument for a deity, but a philosophical demonstration that the multiverse is not the ultimate answer its proponents claim it to be. It reframes the design question rather than resolving it, revealing that our search for a complete, self-contained explanation of existence may be a journey with no final destination. The cultural weight of this idea is immense, blurring the lines between scientific cosmology and age-old metaphysical wonder. This intellectual surrender carries a real and tangible cost for the future of science. The multiverse, for all its grandeur, can function as a kind of philosophical safety net, catching any anomaly that might otherwise force a revolutionary rethink. Imagine a team of explorers confronted by a locked door. One group works tirelessly to pick the lock, convinced a single, elegant mechanism lies within. Another group simply declares that an infinite number of identical rooms must exist elsewhere, and since we are already inside one, there is no need to understand the lock. The multiverse argument can have a similar dampening effect on scientific curiosity. Why struggle to explain why the mass of the electron has its specific, seemingly arbitrary value, if you can simply posit that every possible value exists in some other universe? This mindset risks turning fundamental physics from a dynamic search for answers into a passive cataloging of possibilities. The drive to find a unique, elegant theory of everything, one that explains why our universe must be the way it is, could slowly wither. The danger is not just a pause, but a permanent diversion. Instead of probing the deepest layers of reality, we might content ourselves with mapping the endless surface of a hypothetical multiverse, a map we can never truly verify. This sociological critique suggests the idea's greatest threat may not be to our understanding of reality, but to our courage to pursue it. Yet, this very concern about a dead end reveals a path forward, one that demands we refocus our attention not on unseen worlds, but on the profound uniqueness of our own. Science is a story of revolutions, not conclusions. The very framework we use to describe reality is always provisional, a set of best guesses waiting to be overturned by a deeper truth. The multiverse itself could be the next great paradigm awaiting its own obsolescence. We stand today at a crossroads similar to the one physicists faced in the late 19th century. Back then, Newton's laws seemed to explain everything from the fall of an apple to the orbits of planets. The universe appeared to be a majestic, deterministic clockwork. But a few small anomalies remained, tiny cracks in the Newtonian edifice, like the precise speed of light. It took the genius of Einstein to see that these were not mere cracks. They were glimpses of a completely new reality, a relativistic universe where time and space were woven together into a single fabric. The old model was not just corrected. It was replaced. The multiverse hypothesis may be our generation's Newtonian physics. It is a sprawling, complex framework built to explain the stubborn anomalies of our cosmos, particularly the baffling fine-tuning of the physical constants. But its core premise, the existence of an infinite number of unobservable worlds, is a clear signal that we are missing something fundamental. A true revolution would not add more layers to the cosmic onion. It would reveal that the onion has a different structure altogether. The ultimate goal of physics has always been a theory of everything, a single, elegant set of principles from which all of reality flows. Such a theory would not need an infinity of other universes to explain why ours looks the way it does. It would demonstrate that our universe could not be any other way. The constants would not be arbitrary numbers pulled from a hat. They would be necessary consequences of a deeper logical structure, like the angles of a triangle always adding up to 180 degrees in Euclidean geometry. In this post-multiverse paradigm, the Big Bang would not be a mysterious singularity or a random bubble nucleation. It would be the inevitable outcome of a self-consistent mathematical truth. The multiverse, in this light, would not be proven false. It would simply become irrelevant, an unnecessary complication in a much simpler and more powerful story. Its collapse would mark not a failure of imagination, but a monumental leap in understanding. We would finally see that we were not asking the wrong question, but we were answering it with the wrong tools. The journey to that new horizon will require a courage to look beyond the comfort of infinite possibilities and seek a singular, beautiful truth. At the very frontier of physics lies a chasm so deep it defines our ignorance. We have two magnificent pillars of modern science, general relativity and quantum mechanics, and they speak entirely different languages. One describes the graceful curvature of space-time around planets and galaxies, the other the frantic, probabilistic dance of subatomic particles. Both are spectacularly successful in their own domains, but when forced to meet, in the heart of a black hole or the first instant of the Big Bang, their equations explode into nonsense. This is the quantum gravity bottleneck, the single greatest obstacle to a complete understanding of reality. Our most ambitious ideas about the multiverse are built from the very theories that hit this wall. Cosmic inflation, the engine of the eternal multiverse, is a theory of gravity, but it operates in a realm where quantum effects should be paramount. We are essentially trying to describe the origin of everything using only half the rulebook. It is like trying to understand a symphony by only reading the notes for the string section, completely ignoring the woodwinds, brass, and percussion. The resulting melody might be beautiful, but it is a pale shadow of the full, complex harmony. The string theory landscape, with its 10 to the 500th power possible universes, is another casualty of this bottleneck. String theory was conceived as a theory of quantum gravity, but it has yet to deliver a single, testable prediction. Its vast multiverse is a consequence of mathematics that remains untethered from the physical world, a castle built before its foundation was fully understood. The terrifying possibility is that our entire conception of a multiverse is a mirage, an artifact of our incomplete knowledge. A true theory of quantum gravity might show that the process of eternal inflation is not eternal at all. It could reveal that the quantum foam from which new universes are thought to bubble is unstable, or that the very concepts of before and outside our universe are meaningless without a unified framework. The multiverse, in this light, is not a final destination. It is a temporary scaffold, a placeholder our minds have constructed to bridge the gap in our understanding. It is the best story we can tell with the broken tools we currently possess. When the final theory arrives, it may not describe an infinity of worlds, but a single, coherent cosmos whose beginning and underlying logic are far stranger and more beautiful than we ever imagined. This pending revolution forces us to confront the final and most humbling concept on our list. A disembodied brain, floating in the void, suddenly awakens with a complete set of false memories. It thinks it has a body, a past, a life. It believes it is sitting somewhere, watching a video about the cosmos. This is not science fiction. It is the Boltzmann brain paradox, a logical specter that haunts any vision of an eternal, dying cosmos. The argument stems from the relentless march of entropy, the trend toward disorder. In a universe destined for heat death, a state of maximum randomness, the odds of a fully ordered system like a galaxy or a planet forming by accident are astronomically small. But the odds of a single, conscious brain popping into existence from a random quantum fluctuation are, given enough time, almost certain. In a truly eternal and vast multiverse, these momentary, self-aware fluctuations would outnumber the brains that evolved naturally in stable universes by an unimaginable factor. The conclusion is unsettling. If the standard cosmological model is correct, then you are statistically far more likely to be a Boltzmann brain, a momentary accident with a fabricated history, than a real person in a real, ordered universe. This is more than a philosophical curiosity. It is a direct assault on the logical foundation of our science. Our entire understanding of the cosmos is built on the reliability of our memories and observations. We trust that the past we remember actually happened, that the laws of physics have been constant. But if you are a Boltzmann brain, your memory of reading about the previous 23 concepts is just an illusion, conjured into existence a moment ago. The paradox forces a brutal choice. Either our cosmological picture of an eternal, high-entropy future is fundamentally wrong, or we must accept that our most basic sense of reality is a statistical impossibility. This final, dizzying concept does not just challenge the multiverse. It challenges the very validity of reason itself, pulling the rug out from under every argument we have considered. Taken together, these 24 ideas form a chorus of doubt, each voice singing a different verse in a song about the limits of our current understanding. They are not a list of disproven ideas, but a map of the cracks in a grand, sprawling edifice. From the infinite regress of explanations to the ghostly paradox of the Boltzmann brain, a consistent pattern emerges. The multiverse, proposed as a solution to our deepest mysteries, consistently generates new, deeper mysteries of its own. It pushes the fundamental questions of existence one step further away, but never truly answers them. This collective weight of conceptual challenges suggests we are at a pivotal moment, not unlike the time before Einstein, when the cracks in Newton's universe were visible but not yet understood. The true revolution may not be in discovering an infinite cosmos, but in realizing that our own singular, strange, and finely tuned universe is trying to tell us something far more important. A theory besieged on all fronts begins to buckle under its own contradictions. The horizon of our perception erects a permanent wall. The bedrock of mathematics crumbles into infinite ambiguity, and the very act of observation threatens to splinter reality beyond recognition. These are not isolated critiques. They form a chorus of dissonance, each voice amplifying the others. The philosophical unease of infinite regress finds its physical counterpart in our cosmic isolation. The mathematical crisis of probability is echoed by the existential threat of the Boltzmann brane. The elegant solution proposed by quantum decoherence makes the sprawling many worlds interpretation seem like an extravagant fantasy. When viewed individually, each challenge might be dismissed as a puzzle to be solved later. But together, they weave a tapestry of doubt. The multiverse is not simply facing a few technical difficulties. It is grappling with fundamental limitations that strike at the core of the scientific method itself. This collective weight reveals the popular portrayal of the multiverse as an established fact to be a profound misrepresentation of the truth. It is, instead, a staggering hypothesis born from human ingenuity, a monument to our desire to explain the inexplicable. It represents a frontier of thought, not a destination. This precarious position forces a final, deeply personal question. If the multiverse is not the answer, what does our persistent fascination with it say about our place in the cosmos and the future of our quest to understand it? Our journey through these 24 concepts has not been a demolition, but a deep and necessary excavation. We have seen how the logical foundations of the multiverse can crumble into infinite regress, how the promise of infinite variety shatters against the rocks of uncomputable probability, and how the entire edifice threatens to vanish into a ghostly paradox. The picture that emerges is not of a failed idea, but of a hypothesis stretched to its breaking point, revealing the contours of our own ignorance. This is not a story of scientific failure. It is a celebration of the scientific process at its most ambitious and self-correcting. The multiverse, in all its grandeur and fragility, has served a profound purpose. It has forced us to confront the deepest puzzles of existence, from the nature of consciousness to the ultimate origin of the laws of physics. It has reminded us that our most cherished models of reality are temporary scaffolds, built to be climbed and then dismantled when a firmer structure is found. The true legacy of this exploration may not be a definitive answer about parallel worlds, but a renewed sense of wonder about the singular, strange, and wondrous cosmos we actually inhabit. The greatest mystery is no longer what might lie beyond the horizon of our universe, but the untapped potential of the human mind to unravel the secrets of our own. Thank you for joining this journey to the edge of understanding.